Hello, welcome back to ZzScience. Tonight, we're going to ask a very simple question, one that sounds easier than it really is. Will we ever truly leave the solar system? It's the kind of question that feels straightforward at first. You imagine a spacecraft. You imagine it moving away from the sun. You imagine it crossing some invisible line, far out in the dark, and then it's gone. It's left. It's somewhere else now. But the more you think about it, the less simple it becomes. Because what does it mean to leave? What are we leaving exactly? And how far do you have to go before you can say you've actually done it? These aren't just philosophical questions, they're physical ones. They involve gravity and distance and energy and time. They involve forces that stretch across billions of miles, forces that never quite let go. They involve boundaries that aren't really boundaries at all, but gradual transitions, slow fades from one thing into another. And so tonight, we're going to move slowly through this question. We're going to look at what the solar system actually is, not as a diagram in a textbook, but as a physical region of space with edges that blur and shift. We're going to think about what it means to escape, to leave, to be free of something. And we're going to be careful not to assume too much, because the universe has a way of being more complicated than we expect. Let's start with the most basic version of the question. When we say solar system, what do we mean? Most of us picture the same thing. The sun in the center, Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, maybe Pluto, depending on how we feel about that particular debate. And then, space, empty space, the gap between our sun and the next star. That picture isn't wrong, exactly, but it's incomplete. Because the solar system isn't just a collection of planets, it's a region of influence. It's everywhere the sun's gravity matters. Everywhere the sun's light reaches. Everywhere particles from the sun are moving outward, pushing against the rest of the galaxy. And those things don't stop at Neptune. They don't stop at Pluto either. They keep going, far beyond anything we usually think about when we imagine the edge of our cosmic neighborhood. So if we want to know whether we can leave the solar system, we need to first understand what we're trying to leave behind. And that's harder than it sounds. Let's talk about gravity first. Gravity is the most obvious thing holding us here. The sun is massive, far more massive than anything else nearby, and its gravity pulls on everything around it. That pull is what keeps the planets in orbit. It's what keeps comets falling back toward the inner system after long journeys outward. It's what defines, in the most fundamental sense, what belongs to the sun and what doesn't. But gravity doesn't have a sharp edge. It's not like a fence or a border. You don't cross a line and suddenly feel nothing. Instead, gravity falls off gradually, getting weaker and weaker the farther you go, but never quite reaching zero. The strength of gravity decreases with the square of the distance. If you double your distance from the sun, the gravitational pull becomes 1/4 as strong. If you go 10 times farther, it becomes 1/100th as strong. But even at 100 times the distance, it's still there. Even at 1,000 times, it's still there. Even at 1,000,000 times, technically, mathematically, it's still there. So in a strict sense, the sun's gravity reaches infinitely far. It just becomes unimaginably weak. That makes it hard to define an edge. Because if gravity never actually stops, then there's no distance at which you can definitively say you've escaped it. Now, in practical terms, we do talk about escaping gravity. We talk about escape velocity, and that's a useful concept. Escape velocity is the speed you need to reach in order to coast away from something forever, without ever falling back. For Earth, That's about 7 miles per second. For the Sun, if you're starting from Earth's distance, it's about 26 miles per second. If you reach that speed and you're pointed away from the Sun, then you're done. You don't need to keep accelerating. You can turn off your engines, drift, and you'll keep moving outward. The Sun's gravity will keep slowing you down, but it will never slow you down enough to pull you back. You'll just keep going, slower and slower, but always moving away. That sounds like leaving. It sounds like freedom. But even after you've escaped in that sense, the Sun is still pulling on you. It's pulling on you when you're twice as far as Neptune. It's pulling on you when you're 100 times farther than that. It's pulling on you in a way that, yes, becomes negligible, becomes irrelevant compared to other forces, but it's still there. So have you left? Or have you just gotten far enough that it doesn't matter as much? This isn't a trick question. It's a genuine ambiguity. And it's the first hint that leaving might not be as clear-cut as we'd like. Let's make it more complicated. Gravity isn't the only thing the Sun does. It also emits light. It emits particles. It emits a constant wind of charged particles, protons and electrons, streaming outward in all directions at hundreds of miles per second. This is called the solar wind. And the solar wind creates a kind of bubble around the Sun. Not a physical bubble, not something you could touch, but a region where the solar wind is the dominant thing happening. Inside this bubble, the Sun's particles are moving outward, filling space, pushing against everything they encounter. Outside this bubble, the solar wind fades, and the interstellar medium, the thin gas between the stars, starts to take over. The edge of that bubble is called the heliopause, and it's one of the most natural places to think of as the boundary of the solar system. The heliopause is real. It's measurable. Spacecraft have crossed it. We know roughly where it is, somewhere around 90 to 100 times the distance from the Sun to the Earth. That's about 9 billion miles, maybe 10 billion, depending on the direction and the conditions at the time. That's far. That's much farther than any planet. But it's not infinitely far. It's reachable, at least by machines. So is that the edge? Is that where we leave? Maybe. But there's still more to think about. Because even beyond the heliopause, even in interstellar space, the Sun's gravity is still significant. There are objects out there, far past the heliopause, that are still gravitationally bound to the Sun. They're still orbiting, even if their orbits take thousands or tens of thousands of years to complete. We're talking about the Oort cloud. The Oort cloud is a theoretical shell of icy objects, trillions of them, scattered in a vast spherical cloud around the Sun. We've never directly observed it. We infer its existence from the comets that occasionally fall inward, arriving from random directions, as if they were knocked loose from some distant reservoir. The Oort cloud is thought to extend out to somewhere around 100,000 times the Earth-Sun distance, maybe even 200,000 times. That's roughly a light year. That's a quarter of the way to the nearest star. And everything in the Oort cloud is still orbiting the Sun, still gravitationally bound, still, in a very real sense, part of the solar system. So now we have two possible edges. The heliopause, where the solar wind stops, and the outer edge of the Oort cloud, where the Sun's gravity stops being strong enough to hold on to anything. They're not in the same place, not even close. One is about 10 billion miles. The other is about 6 trillion miles. Which one counts? It depends on what you mean by leaving. If leaving means escaping the direct, immediate influence of the Sun's wind and magnetic field, then crossing the heliopause is enough. You've entered interstellar space. The environment around you is no longer dominated by the Sun. You're in the galaxy's space now, not the sun's. But if leaving means escaping the sun's gravitational control, being truly free to drift away without any lingering connection, then you need to go much farther. You need to get past the Oort cloud, past the last objects that still orbit, past the point where the sun's gravity is weaker than the combined gravity of other nearby stars. And those are very different accomplishments. One is difficult but achievable. The other is, by current technology, almost unimaginably distant. Let's sit with that for a moment. The nearest stars are about 4 light-years away. That's about 25 trillion miles. The outer edge of the Oort cloud might be a quarter of that, maybe 6 trillion miles. So even the farthest reaches of the sun's gravitational influence are still closer to us than the nearest other star. That's worth pausing on, because it means that even if we travel far enough to be in interstellar space, far enough that the sun's wind has faded and the particles around us come from elsewhere, we're still, in a sense, near home. We're still in the sun's neighborhood, still within the sphere of its gravity, even if just barely. And that raises another question, a quieter one, a more subtle one. If leaving is about cutting ties, about becoming independent, then maybe it's not really about distance at all. Maybe it's about trajectories, about intention, about whether you're coming back. Think about the way we talk about orbits. When something is in orbit, it's falling. It's constantly falling toward the thing it's orbiting. But it's also moving sideways fast enough that it keeps missing. That's what an orbit is. A perpetual fall that never lands. The moon is falling toward Earth. Earth is falling toward the sun. The sun is falling toward the center of the galaxy. Everything is falling, endlessly, in circles or ellipses or long, stretched loops. And as long as you're in orbit, you're bound. You're connected. You might be far away. You might take centuries to complete a loop, but you're still part of the system. You're still falling. Leaving, then, means stopping the fall. It means reaching a speed where your trajectory is no longer curved back toward the center. It means moving in a straight line, or near enough to one, that you'll never return. That's escape. But even that isn't perfectly clean. Because in space, nothing moves in a truly straight line. Everything is being pulled by everything else, faintly, constantly. Once you escape the sun, you're still in the galaxy, and the galaxy has gravity too. You're falling toward the galactic center now, in a very slow, very large orbit. You've just traded one orbit for another. So in a cosmic sense, you never really stop falling. You never truly leave. You just change what you're falling toward. That might sound depressing, might sound like we're trapped, like there's no such thing as real freedom in space. But maybe it's better to think of it differently. Maybe leaving isn't about cutting all connections. Maybe it's about moving far enough that the connection becomes something else. A memory, a distant influence, something that shaped you but no longer controls you. You can leave your hometown, you can move across the world, but your hometown still exists. It's still affected who you are. You're still connected to it, in a sense, even if you never go back. Maybe leaving the solar system is like that. Not a clean break, but a slow loosening. A gradual shift from being held tightly to being held gently, to being held so faintly that it barely matters. And maybe that's enough. Let's think about what it would take to do that, not in theory, but in practice. What would it take for a human or a machine made by humans to reach that kind of distance? First, you need speed. Space is big, absurdly big. The distances we're talking about are so large that even light, the fastest thing in the universe, takes years to cross them. Light moves at about 186,000 miles per second, and at that speed, it still takes over 4 years to reach the nearest star. We don't have anything that moves anywhere near that fast. The fastest human-made object right now is a spacecraft called the Parker Solar Probe. It's designed to study the Sun, and it does so by diving very close to the Sun and using the Sun's gravity to accelerate. At its fastest, it reaches speeds of around 120 miles per second. That sounds fast. And it is. It's faster than anything else we've ever built. But it's still less than 1% of the speed of light. At that speed, it would take about 7,000 years to reach the nearest star. 7,000 years. That's longer than recorded human history. That's longer than agriculture. That's so long that the people who launched the spacecraft wouldn't just be dead, their entire civilization might be unrecognizable by the time it arrived. And that's the fastest thing we've made. Most spacecraft move much slower. The Voyager probes, which are the farthest human-made objects from Earth, are traveling at about 38,000 miles per hour. That's fast by everyday standards, but in cosmic terms, it's a crawl. At that speed, it would take something like 70,000 years to reach the nearest star. 70,000 years. Longer than modern humans have existed as a species. So, speed is a problem. A big problem. Maybe the biggest problem. But it's not the only problem. You also need energy. Moving fast requires energy, a lot of energy. And the faster you want to go, the more energy you need. It's not a linear relationship. If you want to go twice as fast, you need much more than twice the energy. The energy required grows dramatically with speed. And we don't have great ways to generate or store that much energy in space. Right now, most spacecraft use chemical rockets. Chemical rockets work by burning fuel and shooting the exhaust out the back, and the force of that exhaust pushes the rocket forward. They're simple, they're reliable, and they're powerful enough to get us off the ground and into orbit. But they're not efficient for long journeys. They run out of fuel quickly, and fuel is heavy, which means you need even more fuel just to carry the fuel, and the whole thing spirals into a problem of diminishing returns. There are better options. Ion drives, for example, use electricity to accelerate ions and shoot them out at very high speeds. They're much more efficient than chemical rockets, but they're also much weaker. They produce a tiny amount of thrust, enough to slowly, gradually build up speed over months or years, but not enough to feel like dramatic acceleration. And even ion drives require power. Solar panels can provide that power, but only near the sun. Farther out, where sunlight is dim, you need something else. Radioisotope thermoelectric generators, maybe, which use the heat from decaying radioactive material to generate electricity. But those are heavy, and they produce limited power, and they eventually run out. Nuclear propulsion has been proposed. Fission reactors, or even fusion reactors, could theoretically provide much more power and much more thrust. But we've never built a working fusion rocket. And even fission rockets, which are more plausible, come with enormous engineering challenges and political complications. The point is, getting up to the kinds of speeds we'd need to leave the solar system in a human lifetime, or even a few human lifetimes, is not something we currently know how to do. We can imagine it, we can sketch it out on paper, but we don't have the technology, not yet, and maybe not for a long time. Then there's the question of why. Why would we want to leave the solar system? That might seem obvious. Exploration, curiosity, desire to see what's out there, to reach for something beyond our current grasp. Those are real motivations, and they've driven human achievement for as long as there have been humans. But leaving the solar system is different from other kinds of exploration. It's different because of the timescales involved. It's different because of the cost. It's different because there's no realistic possibility of return. When explorers sailed across oceans, they could come back. When astronauts landed on the moon, they could come back. Even a mission to Mars, if we ever do it, would probably involve the crew coming back. The journey is long, but it's not impossibly long. It's measured in months or a few years, not lifetimes. But if you send a crewed spacecraft out of the solar system, using anything like current technology, you're not sending people on a journey. You're sending them to live out the rest of their lives in a small, enclosed space, knowing they'll never arrive anywhere. Or, if you're imagining a multi-generational ship, you're asking people to have children who will have children who will have children, all of whom will spend their entire lives in transit, for the sake of a destination that none of them will live to see. That's a very different kind of commitment. And it raises very different ethical and practical questions. Is it worth it? Is it fair? Would people volunteer for that? Would societies invest the resources required for something with no tangible return for hundreds or thousands of years? Maybe. People do surprising things, but it's not obvious. And if we're talking about uncrewed missions, missions with no humans on board, just robots and sensors, then the question shifts again. Because then the purpose is purely scientific. Or maybe symbolic. We're sending a message, a marker, a sign that we were here and we reached outward. That has value, but it's a quieter kind of value, a slower kind, the kind that's hard to justify when resources are limited and problems are immediate. So part of thinking about whether we can leave the solar system is thinking about whether we want to badly enough, whether the desire is strong enough to sustain the effort, given everything else we might do instead. And that's not a question with a single answer. It depends on who you ask. It depends on when you ask. It depends on what else is happening in the world or in the solar system at the time. But let's set that aside for now. Let's assume the will is there. Let's assume we decide, collectively, that this is something worth doing. That we want to send something, human or machine, out past the edges of the sun's influence and into the space beyond. How would we do it? Let's start with the route, the path, the trajectory. You might think the best way to leave the solar system is to point directly away from the sun and accelerate. That makes intuitive sense. You want to get away, so you go in the opposite direction. But that's not actually the most efficient way, because you're not starting from rest, you're already moving. Earth is orbiting the sun at about 67,000 miles per hour. If you launch from Earth, you inherit that motion. You're already going fast, but you're going sideways, not outward. To leave the solar system, you need to either speed up in the direction you're already moving, or slow down, or change your direction. And each of those options requires energy. The most efficient way to leave, it turns out, is to speed up. To add to your existing orbital velocity until you're moving fast enough to escape. That way, you're using the speed you already have, and you're just building on it. This is why spacecraft leaving the solar system tend to launch in the same direction Earth is orbiting, not perpendicular to it or backward. You use Earth's motion as a head start. But even that's not enough. Even if you add a lot of speed, you're still not going fast enough to reach another star in a reasonable time. So you look for shortcuts, ways to gain more speed without burning more fuel. The most common shortcut is a gravity assist. A gravity assist, or gravitational slingshot, is a maneuver where you fly close to a planet and use its gravity to change your speed and direction. You're not stealing energy from the planet exactly, but you're borrowing momentum. You fall toward the planet, whip around it, and fling yourself off in a new direction, faster than you were before. This has been used on almost every mission to the outer solar system. Voyager 1 and Voyager 2 both used gravity assists from multiple planets to accelerate and change course. Without those assists, they wouldn't have had nearly enough speed to reach the outer planets, let alone leave the solar system. But gravity assists have limits. You can only use them if there's a planet in the right place at the right time, and you can only gain so much speed. After a certain point, there's no more planets to help you. You're on your own. So even with the most efficient route, even with multiple gravity assists, you're still looking at very long travel times. Decades to reach the heliopause, millennia to reach the Oort cloud, tens of millennia to reach another star. And during all that time, the spacecraft is moving through space. Empty space mostly, but not perfectly empty. There's dust. There are tiny particles, hydrogen atoms, scattered thin but present. At high speeds, even a tiny particle can cause damage. It's like sandblasting. Over time, over thousands of years, the slow accumulation of impacts could wear down a spacecraft, erode its surfaces, damage its instruments. We don't fully know how serious that problem is because we've never sent anything far enough or fast enough to test it. But it's something to think about. Another challenge, another complication. There's also radiation. Space is full of radiation. Cosmic rays, high-energy particles from distant exploded stars, flying through space at nearly the speed of light. They're rare, but over a long enough journey, you'll encounter them. And they can damage electronics. They can corrupt data. They can, over time, degrade the very systems you need to keep the spacecraft functioning. Shielding helps. But shielding is heavy, and the heavier your spacecraft, the more energy you need to accelerate it. So there's always a trade-off. And then there's the question of communication. Imagine you've sent a spacecraft out past the heliopause. It's in interstellar space now. It's farther from Earth than anything has ever been. And you want to know what it's seeing. You want to receive data. But the signal has to travel back to you at the speed of light. And even light takes time to cross those distances. At the distance of the heliopause, about 10 billion miles, light takes something like 15 hours to arrive. So, if the spacecraft sends a signal, you won't receive it for 15 hours. And if you send a command back, it won't arrive for another 15 hours. That's a 30-hour round trip. That's manageable, if awkward. But as the spacecraft keeps moving, the delay gets longer. A day, 2 days, a week, a month. Eventually, communication becomes so slow that it's almost meaningless. You're not having a conversation, you're exchanging messages across a gulf of time as well as space. And the signal gets weaker too. Radio signals spread out as they travel. By the time they've crossed billions of miles, they're incredibly faint. You need very large antennas, very sensitive receivers, just to pick them up. And even then, there's noise, interference, the faint hiss of the universe. The Voyager spacecraft are barely detectable now. They're still sending signals, but those signals are so weak that only the largest radio dishes on Earth can hear them. And they're powered by radioactive decay, which is slowing down. In a few more years, maybe a decade or two, they won't have enough power to transmit. And then they'll go silent. They'll still be out there, still moving, still leaving. But we won't know what they're experiencing. We won't know if they've encountered anything unusual, if they've passed through some unexpected region of space. They'll be alone in the dark, beyond our reach, beyond our knowledge. Is that still exploration? Or is it just sending something away? That's a question without an easy answer, because exploration usually involves bringing information back, sharing what you've learned. If there's no way to communicate, if the thing you've sent is functionally lost, then in a sense, nothing has been explored. At least, not by us. But maybe there's value in the sending itself, in the act of reaching, in knowing that something we made is out there, continuing outward, even if we never hear from it again. There's a kind of poetry to that, a quiet dignity. But it's not the same as the exploration we usually imagine. Let's zoom out for a moment. Let's think about this from a broader perspective. We're talking about leaving the solar system as if it's a single, definable goal, as if there's a finish line. But maybe it's better to think of it as a continuum, a gradual progression. Near Earth, the sun is overwhelming. It's bright, it's hot, its gravity dominates. There's no question that you're in the solar system. You're in the thick of it. As you move outward, things change. The sun gets dimmer, its gravity weakens. The solar wind thins out, but you're still clearly within its influence. You're still in the solar system. At some point, you cross the heliopause. The solar wind fades, the interstellar medium takes over. You're in interstellar space. But the sun's gravity is still significant. Objects still orbit. You're still part of the sun's domain. Farther out, in the Oort cloud, the sun is just a bright star among other stars. Its gravity is still present, still enough to hold on to distant comets, but it's weak, fragile. A nudge from a passing star could disrupt it. And beyond the Oort cloud, the sun's gravity becomes indistinguishable from the collective gravity of nearby stars. You're no longer orbiting the sun in any meaningful sense. You're adrift, free. Or as free as anything can be in a galaxy full of gravity. So there's no single moment where you leave. There's no sharp boundary. There's just a slow transition from being close to being far, from being held tightly to being barely held at all. And maybe that's the real answer to the question. Not, can we leave, but how far can we go before it stops feeling like home? Because the solar system isn't just a physical region. It's also a psychological one. It's where we come from. It's where all of human history has happened. It's the only environment we've ever known, in any direct, lived sense. Even the moon, which we've visited, is part of the solar system, part of our local neighborhood. It's just a few days away. It's close enough to see with the naked eye, close enough to feel connected to. Mars, if we ever reach it, will be farther, several months away, depending on the alignment. But it's still a planet, still a place you could, in theory, stand on, still something that feels like a destination. But beyond that, beyond the planets, space stops feeling like a place and starts feeling like an abstraction. It's too big, too empty, too far removed from anything familiar. And if you're traveling through that space, on a journey that will last longer than your lifetime, longer than many lifetimes, then the solar system stops being a place you've left and starts being a place you're leaving. A process, not an event. You carry it with you. In your trajectory, in your origin, in the direction you came from. And maybe you never fully leave, because part of you is always connected to where you started. Even if the connection is just memory, even if it's just the fact that you once were there and now you're here, and the distance between those two things is what defines you. That's a more human way to think about it. Less about physics, more about meaning. But the physics still matters. The physics is what makes it hard. The physics is what makes it take so long. Let's come back to that. Let's talk about the obstacles. The real, practical, tangible reasons why leaving the solar system is so difficult. We've talked about speed. We've talked about energy. We've talked about time. But there's another issue. One that's easy to overlook because it's so fundamental. You need to survive the journey. If you're sending a machine, that means keeping it functional, keeping its electronics working, keeping its power source active, keeping its instruments calibrated, keeping its antenna pointed at Earth, or at least pointed in a direction where it can send back data. All of those things degrade over time. Bearings wear out, circuits fail, radiation damages components, software encounters unexpected bugs, unexpected conditions that the programmers didn't anticipate. The Voyager spacecraft are engineering marvels. They were built in the 1970s, designed to last 5 years, and they've now been operating for over 45 years. That's an incredible achievement. But they're failing. Slowly, gradually, one system at a time. Instruments have shut down. Heaters have stopped working. Power is running low. They won't last much longer. Another decade, maybe. And then they'll be inert. Still traveling, still moving outward, but no longer functioning. No longer sending back data. Just debris, essentially. Very expensive, very distant debris. And if that's the fate of our best, most carefully designed deep space probes, what does that say about the prospects for longer missions? For missions that need to last not decades, but centuries or millennia. It says we need better technology, more robust systems, redundancy, self-repair, or maybe a completely different approach. Some people have proposed sending probes that are intentionally simple, small, lightweight, with minimal electronics, minimal moving parts. The idea being that the simpler something is, the less there is to break. Others have proposed the opposite. Sophisticated, self-repairing machines. Robots that can diagnose problems and fix themselves. Artificial intelligence that can adapt to unexpected situations. Both approaches have merit. Both have challenges. Neither has been tested over the timescales we're talking about. And if you're sending humans, the problem becomes vastly more complicated. Because humans need air, food, water, warmth, pressure, gravity, or at least something to counteract the effects of long-term weightlessness. Medical care, social interaction, purpose. You need to create a completely self-sustaining environment, a tiny Earth enclosed in metal and plastic, hurtling through the void. We've never done that. Not for more than a year or two. The International Space Station is impressive, but it's supplied regularly. From Earth. It's not self-sustaining. And it's still close enough that if something goes seriously wrong, people can come home. On a journey out of the solar system, there's no resupply. There's no going home. You're on your own. For decades. For generations. The technical challenges are immense. The psychological challenges might be even greater. Humans aren't evolved for that kind of isolation, that kind of confinement. We're social creatures. We're adapted to wide open spaces, to horizons, to the rhythms of day and night. Spending your entire life in a small enclosed space, seeing the same few dozen people every day, knowing you'll never see anything new, never set foot on solid ground. That's a hard thing to ask of anyone. And yet, people have suggested it. People have designed generation ships, at least on paper. Ships large enough to support a small population. With farms, with living quarters, with schools and workshops, and everything a tiny society would need. The idea is that the first generation accepts the journey willingly. They know they won't reach the destination, but they're okay with that. They're pioneers. They're making it possible for their children or their children's children to arrive somewhere new. But what about those children? What about the people born on the ship, who never chose to be there, who've never seen Earth, never walked under an open sky, never had the option to live anywhere else? Are they explorers, or are they prisoners? That's an uncomfortable question, and it's one of the reasons why, despite all the designs and all the speculation, no one has actually built a generation ship. It's not just a technical problem, it's an ethical one. Maybe it's better to wait, to develop better propulsion, faster engines, shorter journeys, so that the people who leave might actually arrive. Or maybe it's better to send machines. Let them do the exploring. Let them send back the data, and we can experience it vicariously from the safety and comfort of home. There's no shame in that. Machines are good at this. They don't get bored. They don't need food. They don't care about the isolation. And if they fail, it's sad, but it's not tragic. Not in the way that losing human lives would be tragic. But machines can't wonder. They can't feel awe. They can't look out at the stars and feel the weight of the distance, the strangeness of being so far from everything familiar. And maybe that matters. Maybe the experience of exploration is part of the point. Not just the data, but the feeling, the human connection to the journey. Or maybe it doesn't matter. Maybe the data is enough. Maybe knowing is enough, regardless of who or what does the knowing. These are questions without clear answers, and they're part of what makes the question of leaving the solar system so complex. Because it's not just about whether we can, it's about whether we should, and why, and what it would mean. Let's think about another aspect of this, the idea of return. Most exploration throughout history has involved going somewhere and coming back. You sail across the ocean, you find new land, and then you sail home to tell people about it. You climb a mountain, you reach the summit, and then you climb back down. Even the Apollo missions to the moon followed that pattern. Go, explore, return. The return is part of the mission. It's how the knowledge gets shared. It's how the explorers are celebrated. It's proof that the journey was real, that it happened, that it was worth doing. But leaving the solar system, at least with current or near-future technology, means giving up on return. The distances are too great. The energy required to slow down, turn around, and come back is more than the energy required to leave in the first place. If you leave, you're gone. Permanently. That changes the nature of the endeavor. It's no longer exploration in the traditional sense. It's more like emigration or exile. You're not visiting. You're departing. And that makes it harder to justify, harder to celebrate. Because there's no triumphant homecoming. There's just a slow fade into distance and silence. Unless, of course, you redefine what return means. Maybe return isn't physical. Maybe return is the signal, the data, the message sent back across the light years, telling us what's out there. That's a kind of return, a virtual one. The spacecraft doesn't come back, but the information does. And in a sense, the information is what matters, the knowledge, the understanding. So maybe we don't need the object to return. Maybe we just need the message. But even that has limits. Because as we've discussed, the farther you go, the weaker the signal, the longer the delay. Eventually, communication becomes impossible, and then even the virtual return is gone. You're left with something that has departed and will never, in any form, return. Is that still exploration? Or is it something else? An offering, maybe? A gift to the universe? A statement that we were here, we tried, we reached outward. There's something poignant about that, something almost melancholy, but also something beautiful. The idea that we might send something of ourselves out into the cosmos, not expecting anything back, just for the sake of doing it. That's a very human impulse. To reach, to explore, to leave a mark. Even if no one ever sees it, even if it accomplishes nothing practical. Just because we can, because we want to, because it feels important. And maybe that's enough of a reason. Maybe that's the best reason. But it still doesn't make it easy. It doesn't solve the technical problems. It doesn't make the distances shorter or the speeds faster. It doesn't change the fact that leaving the solar system, truly leaving, is one of the hardest things we could possibly attempt. Let's think about timescales again. Really sit with them. Let them sink in. Voyager 1 launched in 1977. It's been traveling for over 45 years, and it's only just crossed the heliopause. It's in interstellar space, yes, but it's nowhere near the outer edge of the Oort cloud. It won't reach that for tens of thousands of years. Tens of thousands of years. That's longer than civilization. That's longer than written language. That's longer than cities and agriculture and everything we think of as human history. And that's just to reach the edge of the sun's gravitational influence. Not to reach another star. Not to arrive anywhere. Just to get past the last of the sun's orbiting debris. The nearest star, Proxima Centauri, is about 4.2 light-years away. At Voyager's current speed, it would take about 70,000 years to get there. 70,000 years ago, humans were still in the Stone Age, still living in small groups, still figuring out tools and fire and language. If a Voyager-speed spacecraft had left Earth back then, heading toward Proxima Centauri, it still wouldn't have arrived. It would still be in transit, still crossing the empty space between stars. That's the scale we're dealing with. That's the reality of interstellar travel. It's not just hard, it's almost incomprehensibly slow. And that's with a spacecraft that's already faster than most. That's with something that was designed to leave, that used multiple gravity assists, that was given every advantage we could manage. If we want to do better, we need new technology, new physics maybe, something that can move us orders of magnitude faster. There have been proposals, concepts, ideas that sound almost like science fiction, but are grounded, at least loosely, in real physics. Solar sails, for example. Large, reflective sails that catch the pressure of sunlight and use it to accelerate. They're slow to start, but they don't need fuel. They can keep accelerating as long as there's light. And if you make the sail large enough and the spacecraft light enough, you can eventually reach significant speeds. Laser-pushed sails are a variation on that idea. Instead of using sunlight, you use a powerful laser aimed from Earth or from a satellite to push the sail. You can focus the laser, make it brighter, push harder. In theory, you could accelerate a very lightweight probe to a significant fraction of the speed of light. That's the idea behind projects like Breakthrough Starshot. Send tiny probes, each weighing just a few grams, equipped with a light sail. Push them with an enormous laser, accelerate them to 20% of the speed of light. At that speed, They could reach Proxima Centauri in about 20 years. 20 years. That's fast. That's within a human lifetime. That's something you could watch leave and watch arrive. But there are enormous challenges. The laser would have to be incredibly powerful. The sail would have to be incredibly light and incredibly strong. The probe would have to survive the acceleration, survive the journey, survive the impact of interstellar dust at 20% of light speed. And it would have to send back data across 4 light years with a power source that weighs less than a grape. It's ambitious, maybe too ambitious. But it's not impossible. It's just very, very hard. And even if it works, even if we manage to send a tiny probe to another star, that's not the same as sending humans. Humans are heavy. Humans need life support. Humans can't survive 20% of light speed acceleration. The forces would tear a body apart. So for human travel, we're back to slower speeds. Back to generation ships, or suspended animation, or something we haven't thought of yet. Or maybe we don't send humans at all. Maybe we accept that humans are too fragile, too needy, too tied to Earth, and we send our creations instead. Our machines, our artificial intelligences, our proxies. They could be designed for the journey, built to last, built to think and explore and report back. They wouldn't be us, but they'd be from us, extensions of our curiosity, our ambition, our need to know. Would that be enough? Would that count as leaving? Maybe. It depends on what you value. If you value the experience, the human presence, then no. But if you value the knowledge, the discovery, then maybe yes. This is part of what makes the question so rich, so layered. Because it's not just a technical question, it's a philosophical one. A question about what matters, about what we're trying to achieve, about what it means to be human in a universe that's so much larger than us. Let's return to gravity for a moment, because we started there and it's worth thinking about again. Gravity is often described as a force, and it is, in a practical sense. It pulls things together. It makes things fall. But in a deeper sense, gravity isn't a force at all. It's a curvature of space. The presence of mass bends space, and objects follow the curves. They move along the paths that space allows. The sun bends space around itself. A lot. And that bending is what we experience as the sun's gravity. When you're close to the sun, the bending is steep. The curves are tight. It's hard to escape. You'd have to move very fast, very deliberately, to climb out of the well. When you're far from the sun, the bending is gentle. The curves are shallow. It's easier to escape. You don't need as much speed. But the bending never completely stops. It just gets flatter and flatter, blending into the bending caused by other objects, other stars, the galaxy itself. So in a sense, you're always in some kind of well, some kind of curve. Space is never perfectly flat. There's always something pulling, always something bending the path. And that means escape is always relative. You escape one well, but you're still in another. You leave the solar system, but you're still in the galaxy. You leave the galaxy, but you're still in the local group. And so on, outward, in ever larger scales. There's no final escape, no place where space is perfectly flat and nothing pulls on you. You're always falling, just slowly, gently, towards something distant. And maybe that's okay. Maybe that's just the nature of existence in a universe with mass, with structure, with things. You're never truly free in an absolute sense, but you can be free enough. far enough that the pull is negligible, that it doesn't control you, that you can ignore it for all practical purposes. And maybe that's what leaving the solar system means. Not cutting all ties, not achieving some perfect independence, just getting far enough that the sun's pull is one among many, that it's no longer the dominant thing, that you're no longer defined by it. That's a softer definition, a less dramatic one, but maybe it's more honest. Because in space, nothing is absolute. Nothing is perfectly clean. Everything is gradual. Everything is relative. And if we're going to leave, if we're going to truly understand what that means, we need to accept that. We need to let go of the idea of sharp boundaries and clear endpoints. We need to embrace the blurriness, the ambiguity. We're not leaving a room. We're not crossing a border. We're fading into distance, slowly, over time, with no single moment where we can say definitively that we're gone. And maybe that's beautiful in its own way. A slow departure, a gradual release, a journey that doesn't end so much as continue endlessly into the vast quiet of space. This is ZzScience, and tonight we're thinking about leaving, about what it means, about what it takes, about whether we can and whether we will, and what happens if we do. There's no final answer yet, no conclusion, just questions, and distance, and time, and the slow, patient pull of gravity stretching across billions of miles, never quite letting go. We've been talking about what it means to leave, about boundaries that blur and distances that stretch, about gravity that never quite stops pulling, no matter how far you go. But now let's talk about what we've actually done. Not in theory, not in imagination, but in practice, with metal and circuits and fuel, with spacecraft we've built and launched and watched disappear into the dark. Because we have left, in a sense, not with people, not yet, but with machines, with probes and instruments and cameras, with pieces of human engineering that have traveled farther than anything else we've ever made. And those machines have stories. They have journeys. They have limits and achievements and quiet failures. They're out there right now, moving through space, carrying a little piece of us into the vast emptiness beyond the planets. So let's talk about them. Let's talk about how far we've actually gone. The farthest human-made object from Earth is a spacecraft called Voyager 1. Voyager 1, launched on September 5th, 1977. That's over 47 years ago now. It was built to study Jupiter and Saturn, to fly by them, take pictures, measure their magnetic fields, analyze their atmospheres. That was the primary mission. That's what it was designed for. But the engineers knew, or at least hoped, that if everything went well, Voyager might keep going, might travel beyond the planets, might become something more than just a planetary probe. And it did. Voyager 1 reached Jupiter in March of 1979. It sent back stunning images. Swirling clouds, the Great Red Spot, moons with volcanoes and ice. It was a revelation. Jupiter stopped being an abstract point of light and became a place. A real, complex, beautiful place. Then it moved on to Saturn. Arrived in November of 1980. More images, more discoveries. The rings, impossibly thin and detailed. Moons with strange surfaces, ancient and battered. Titan, with its thick atmosphere hiding whatever lay beneath. And then, Voyager 1 did something unusual. It used Saturn's gravity to fling itself upward, out of the plane of the solar system. It didn't continue on to Uranus and Neptune like its twin, Voyager 2, would. Instead, it headed north, above the ecliptic, gaining speed, leaving the realm of the planets behind. That was the beginning of its true journey, the journey outward. And it's been traveling ever since. For over 40 years now, moving at about 38,000 miles per hour, 17 kilometers per second. Fast by any ordinary standard, but slow in cosmic terms. It's now about 15 billion miles from Earth. That's roughly 24 billion kilometers. That's about 160 times the distance from Earth to the Sun. At that distance, the Sun looks like a very bright star. Not a disk, not something that fills the sky, just a point of light. Brighter than anything else, yes, but still just a point. And the light from the Sun, even, though it's still bright by the standards of starlight, is weak. Too weak to power solar panels effectively. Voyager doesn't use solar panels. It uses something else. Something that doesn't depend on sunlight. It carries 3 radioisotope thermoelectric generators, RTGs. These are devices that convert heat into electricity, and the heat comes from the radioactive decay of plutonium-238. When Voyager launched, those RTGs produced about 470 watts of power, enough to run the spacecraft, power the instruments, heat the electronics, send signals back to Earth. But plutonium decays, slowly, predictably, and as it decays, it produces less heat. And less heat means less power. After 47 years, Voyager's RTGs are producing less than half their original power. About 220 watts now, maybe less. And that number keeps dropping. Every year, Voyager loses about 4 watts. 4 watts doesn't sound like much. It's about the power of a small LED bulb. But when you only have 200 watts to work with, every watt matters. The engineers have had to make hard choices. Turn off instruments, shut down heaters, disable systems that aren't absolutely essential. Anything to conserve power. Anything to keep the spacecraft alive a little longer. Because once the power drops too low, Voyager will go silent. It won't have enough electricity to run its radio transmitter. And once that happens, we'll lose contact. Permanently. That's expected to happen sometime in the next few years. Maybe around 2026 or 2027. Maybe a little later, if they're lucky, if they can squeeze out a few more watts by shutting down something else. But it's coming. The end of Voyager's voice. After that, Voyager will still be out there, still moving, still traveling outward, but it will be silent, unreachable. A piece of human technology, drifting through space, with no way to tell us what it's experiencing. That's a strange thought. Something we made, something we launched with purpose and care, continuing on without us. Without communication, without acknowledgement. Just moving endlessly through the dark. But before that happens, before the power runs out, Voyager has already achieved something remarkable, something historic. On August 25th, 2012, Voyager 1 crossed the heliopause. The heliopause, the boundary where the solar wind stops, where the sun's influence fades and the interstellar medium takes over. This wasn't obvious at first. There's no sign, no marker, no sudden change you can point to and say, definitively, that's the edge. Instead, the scientists had to look at the data, at the particles Voyager was detecting, at the magnetic fields, at subtle shifts in the environment. They noticed that the solar wind particles, the ones streaming outward from the sun, had dropped to nearly zero. And at the same time, the cosmic rays, the high-energy particles from outside the solar system, had increased. That was the sign. That was the transition. Voyager 1 had entered interstellar space. It was the first human-made object to do so. The first thing we'd ever built that had left the sun's bubble and entered the space between the stars. That's worth pausing on, worth reflecting on, because it's an extraordinary achievement, not just technologically, but conceptually. We sent something beyond the sun's direct influence. We reached outside our local environment and touched the broader galaxy. And Voyager 2 followed. It crossed the heliopause on November 5, 2018, 6 years after Voyager 1. Crossing at a different location, at a different time, confirming that the boundary was real, that it wasn't just a fluke or an artifact of the data. So now we have two objects in interstellar space. Two machines, built by humans, traveling through the galaxy's medium, no longer shielded by the sun's wind. But here's the thing. Here's the complication. Crossing the heliopause doesn't mean leaving the solar system. Not entirely. We talked about this before, about how the solar system is more than just the heliosphere, about how the sun's gravity extends much farther, about the Oort cloud, that vast shell of icy objects still orbiting, still bound. Voyager is in interstellar space. That's true. That's accurate. But it's still gravitationally bound to the sun. It's still within the sun's sphere of influence. And it will be for a very long time. At its current speed, Voyager 1 won't reach the inner edge of the Oort cloud for about 300 years. And it won't reach the outer edge for about 30,000 years. 30,000 years. That's an almost incomprehensible span of time. Longer than recorded history. Longer than agriculture. Longer than anything we usually think of as human timescales. And even then, even after 30,000 years, Voyager won't arrive anywhere. It won't reach another star. It will just be drifting through the space between stars, slowly, silently, for thousands more years after that. The nearest star to Voyager's trajectory isn't Proxima Centauri. It's a star called AC plus 793888. It's a small, dim star, not visible to the naked eye, and Voyager 1 will pass within about 1.6 light-years of it. But that won't happen for about 40,000 years. 40,000 years from now. Longer than modern humans have existed. Longer than art and language and culture. By the time Voyager passes that star, if humanity still exists, we'll be unrecognizably different. Our civilizations will have risen and fallen. Our technologies will have evolved beyond anything we can currently imagine. And Voyager will still be out there, drifting, a silent relic from the late 20th century. That's both humbling and inspiring. Humbling because it shows how small we are, how brief our lives are compared to the timescales of the cosmos. Inspiring because it shows that we can create things that last, things that endure, things that continue long after we're gone. Voyager 2 has a different trajectory. It's heading in a different direction. It will pass near a star called Ross 248 in about 40,000 years as well. Different star, similar timescale. Same slow drift through the interstellar void. And both voyages carry something unique, something deliberate, something that says more about us than any scientific data. The Golden Record. The Golden Record is a phonograph record, gold-plated copper, 12 inches in diameter. It contains sounds and images from Earth, music, greetings in multiple languages, natural sounds, whale songs, wind, rain, thunder, footsteps, laughter, a mother's first words to her child. It also contains images, encoded in analog form, Pictures of Earth, of humans, of our cities and our landscapes, of DNA and mathematical definitions and the structure of atoms. Instructions on how to play the record. A map showing Earth's location relative to nearby pulsars. It's a message. A message to anyone or anything that might someday find Voyager. A message that says, we were here, we existed, this is who we were. The chances of anyone finding it are incredibly small. Space is vast, Voyager is tiny, and it's not headed toward anything in particular. It's just drifting. The odds of it being intercepted by another civilization are almost zero. But almost zero isn't zero. And even if no one ever finds it, even if it drifts for billions of years through empty space, never coming close to anything, there's still value in the gesture. In the act of sending a message, even if you don't know if anyone will receive it, it's a way of saying that we care, that we think about our place in the universe, that we want to reach out, to communicate, to be known. Carl Sagan, one of the scientists involved in creating the Golden Record, described it as a message in a bottle, cast into the cosmic ocean, not expecting a reply, but hoping. Hoping that someday, somehow, someone might find it and understand. That's a beautiful idea, a hopeful one. But it's also tinged with melancholy, because it acknowledges our isolation, our loneliness, the vast distances that separate us from anything else that might be out there. We send a message because we can't go ourselves. Not yet. Maybe not ever. And the message will outlast us. Long after humanity is gone, long after Earth is gone, long after the sun has burned out and become a cold, dark cinder, Voyager will still be out there, still carrying that record, still moving through space. A monument, a memorial, a whisper from a vanished world. Let's talk about the other spacecraft, the other objects we've sent outward, because Voyager isn't alone. There are other human-made objects leaving the solar system. Not many, but a few. There's Pioneer 10 and Pioneer 11. The Pioneers launched before the Voyagers. Pioneer 10 in March of 1972. Pioneer 11 in April of 1973. They were the first spacecraft to visit Jupiter, the first to cross the asteroid belt, the first to send back close-up images of the outer solar system. And like the Voyagers, they kept going after their primary missions were complete. They continued outward into the deeper reaches of space. But we've lost contact with them. Pioneer 10's last signal was received in January of 2003, over 20 years ago. Pioneer 11's last signal was in November of 1995, almost 30 years ago. They're still out there, still moving, still traveling at tens of thousands of miles per hour. But they're silent now. Their power has run out. Their transmitters are dead. We don't know exactly where they are. We can estimate, based on their last known trajectories, but we can't track them. We can't confirm. They've disappeared into the dark, beyond our ability to observe or communicate with. Pioneer 10 is heading toward the constellation Taurus. It won't come close to any stars for a very long time, maybe 2 million years before it passes near a star in that direction. Pioneer 11 is heading toward the constellation Aquila, similar timescales, similar isolation. And they also carry messages, not as elaborate as the Golden Record, but messages nonetheless. Plaques, gold anodized aluminium plaques, with engravings showing the spacecraft, showing humans, showing our location in the galaxy. A simpler message than the Voyagers, but the same intent. To say, we were here. So that's 4 spacecraft, 4 objects that have left or are leaving the solar system. But there are more. New Horizons is another one. New Horizons launched in January of 2006. Its mission was to visit Pluto, to be the first spacecraft to see that distant, icy world up close. And it succeeded. In July of 2015, New Horizons flew past Pluto, sending back images that were stunning, revelatory. Pluto wasn't just a fuzzy dot anymore, it was a world. A complex, beautiful, geologically active world with mountains of ice and vast plains of frozen nitrogen and a heart-shaped region that captured the public's imagination. After Pluto, New Horizons continued into the Kuiper Belt. In January of 2019, it flew past a small object called Arakoth, a strange, snowman-shaped object, untouched since the solar system's formation. The most distant object ever visited by a spacecraft. And now, New Horizons is continuing outward, heading away from the Sun. Not as fast as the Voyagers, but fast enough, about 33,000 miles per hour. It's expected to cross the heliopause sometime in the 2040s. Another few decades, another object entering interstellar space. But like the Voyagers, its power is limited. It uses an RTG, and that RTG is decaying. By the time it crosses the heliopause, it might not have enough power to send data. It might already be silent. Or maybe the engineers will find a way to keep it alive a little longer, to squeeze out a few more years of operation. They've been clever before, they might be clever again. But eventually, inevitably, New Horizons will go quiet. And it will join the Voyagers and the Pioneers in the silent fleet of spacecraft drifting through interstellar space. There's also the Parker Solar Probe. Parker is unusual. It's not leaving the solar system. Not directly. Instead, it's diving toward the Sun, getting closer to the Sun than anything else we've ever built. Studying the Sun's corona, the Sun's magnetic field, the origin of the solar wind. But here's the interesting part. Parker is moving very fast, absurdly fast. At its closest approach to the Sun, it reaches speeds of over 400,000 miles per hour, 120 miles per second, faster than any other human-made object. And after its mission is complete, after it's made all its close passes to the Sun, it will still have that speed. It will be on an orbit that takes it far from the Sun, out past the planets. It won't be aimed at anything in particular, but it will be moving fast, fast enough that eventually it might escape the solar system. We don't know for sure. Its trajectory depends on its final orbit, on the exact details of its last solar approach. But it's possible. Another spacecraft joining the outbound fleet decades from now. That would bring the total to 6. 6 spacecraft leaving the solar system or on their way to leaving. 6 objects carrying human engineering, human ambition, human curiosity into the space beyond the Sun's reach. 6 out of thousands. Because we've launched thousands of spacecraft, thousands of satellites, thousands of probes, and only 6 have gone far enough, fast enough to leave. That tells you something about how hard it is, how much energy it takes, how rare and difficult an achievement it is. Most spacecraft stay close to Earth, in low orbit, in geostationary orbit, a few hundred miles up or a few thousand. Close enough that they're still firmly within Earth's gravity well. Close enough that, if they stopped functioning, they'd eventually fall back, burning up in the atmosphere. Some go farther, to the Moon, to Mars, to the inner planets. But even those stay within the inner solar system, within the familiar realm of rock and metal and sunlight. Only a handful go beyond, to the outer planets, to the edge of the heliosphere, to interstellar space. And none have gone quickly. Let's think about that, about the timescales, about how long it takes to reach even the boundaries we've reached. Voyager 1 took 35 years to reach the heliopause, 35 years of continuous travel, 35 years at 38,000 miles per hour. New Horizons, which is faster in some ways, will take about 40 years, maybe longer. That's a significant chunk of a human lifetime. If you were 20 years old when Voyager launched, you'd be 55 when it crossed the heliopause. You'd have gone from young adulthood to middle age. You might have raised children, retired, watched the world change around you. And the entire time, Voyager was out there, moving, slowly, steadily, crossing billions of miles. That's the pace of deep space exploration. Not days or months, but decades. Not within a career, but across a generation. And that's just to reach the heliopause, just to cross the first major boundary. The Oort cloud is still hundreds or thousands of years away. Other stars are tens of thousands of years away. Those timescales are hard to grasp, hard to plan around, hard to stay motivated about. If you start a project that won't see results for 30,000 years, will you care? Will anyone care? Will society invest resources in something that won't pay off for hundreds of generations? It's not obvious that the answer is yes. And yet, we did launch Voyager. We did send it outward, knowing that it would take decades just to reach interstellar space, knowing that it would never return, knowing that the people who built it would be long dead before it reached its true destination, whatever that destination might be. So maybe we can care about long timescales. Maybe we can commit to journeys that outlast us. Maybe there's value in that. In starting something you won't finish. In contributing to something larger than yourself. But it's hard. It requires patience, faith, a belief that the future matters, even if you won't be there to see it. Let's talk about communication, about the signals, about how we know what Voyager is experiencing. Voyager sends data back to Earth using radio waves. Specifically, it uses a high-gain antenna, about 12 feet in diameter, pointed at Earth. The antenna transmits at about 20 watts. That's not much power. About the same as a dim light bulb. But 20 watts is enough if the receivers on Earth are sensitive enough. And they are. NASA uses the Deep Space Network, a collection of enormous radio antennas located in California, Spain, and Australia. Each antenna is about 70 meters in diameter. That's 230 feet. Massive, huge, capable of detecting incredibly faint signals. And even then, Voyager's signal is barely detectable. By the time it reaches Earth, after traveling 15 billion miles, the signal has spread out, weakened, faded to almost nothing. The power density is measured in attowatts per square meter. Trillionths of a watt. It's astonishing that we can detect it at all, that we can pull meaningful data out of that faint whisper, that tiny ripple in the electromagnetic noise of space. But we can, just barely. And as long as Voyager has power, as long as its transmitter is running, we can hear it. But the signal is getting weaker. Not because the transmitter is failing, though that's part of it, but because of distance. Every day, Voyager moves farther away. And every day, the signal has farther to travel. And the farther it travels, the more it spreads, the weaker it becomes. There will come a point where the signal is too weak to detect, where even the most sensitive antennas can't pull it out of the noise. That might happen before the power runs out. Or it might happen after. It depends on the exact details, on how well the transmitter holds up, on how much power is left, on whether there are any unexpected failures or degradations. But either way, silence is coming. Soon. Within the next few years, probably. Maybe a decade at most. And once that happens, Voyager will still be out there. Still functioning maybe, at least partially. Still recording data. But with no way to send it back. No way to tell us what it's seeing. It will be alone. Truly alone. In a way that's hard to think about without feeling a little sad. We built it. We launched it. We guided it. We've been in contact with it for over 40 years. And then, one day, the contact will stop. The conversation will end. And Voyager will continue without us. That's the nature of deep space exploration. At some point, you have to let go. You have to accept that the thing you've sent is beyond your reach, beyond your control, beyond your knowledge. It's still yours in a sense. You made it. You're responsible for it. But it's also independent now, free, traveling through a realm you can't access, experiencing things you can't share. That's a strange relationship, a mixture of pride and loss, of accomplishment and letting go. But maybe that's what exploration always involves, sending something out, hoping for the best, and accepting that it might not come back. Let's think about what Voyager has actually told us, what we've learned from those decades of data, from those faint signals crawling back across the solar system. We've learned about Jupiter, about its magnetosphere, its radiation belts, its moons, about Io with its sulfur volcanoes, about Europa with its icy crust and the ocean that might lie beneath. We've learned about Saturn, about its rings, impossibly thin and complex, about its moons, tight with its methane lakes, Enceladus with its geysers of water ice shooting out from cracks in the surface. We've learned about the heliosphere, about its shape, its boundaries, its interaction with the interstellar medium, about the termination shock, where the solar wind slows down, about the heliosheath, the region between the termination shock and the heliopause, about the heliopause itself, that boundary where the sun's wind stops and the galaxy's wind begins. We've learned that interstellar space is different from what we expected, that the magnetic field has a different orientation, that cosmic rays are more intense, that there are structures, variations, things we didn't predict. All of that knowledge came from Voyager, from those tiny, fragile machines built with 1970s technology, still functioning decades later, still sending back data. It's remarkable. It's a testament to good engineering, to careful design, to redundancy and robustness, and a little bit of luck. But it's also a testament to patience, to long-term thinking, to the willingness to start a project knowing you might not live to see its end. The scientists who designed Voyager, who planned the mission, who built the instruments, many of them are retired now. Some have passed away. They've spent their entire careers, their entire lives, working on this one project. And they've watched it succeed. They've watched it exceed every expectation. They've watched it become more than they imagined. That must be deeply satisfying. To create something that outlasts you, that continues your work long after you're gone. But it's also bittersweet, because they won't see the end. They won't know what happens to Voyager in 100 years, in 1,000 years, in 40,000 years when it passes near that distant star. They've started something they can't finish, and that takes a particular kind of courage, a particular kind of faith. It's the same faith that drives all long-term thinking, all projects that span generations, building cathedrals that take centuries to complete, planting trees whose shade you'll never sit in, launching spacecraft towards stars you'll never see. It's the faith that the future matters, that what you do now will ripple forward, that your contribution, however small, is part of something larger. And maybe that's enough. Maybe that's the answer to the question of why we do this, why we explore, why we reach outward, even knowing we might never arrive. Because the reaching itself matters. The attempt, the effort, the fact that we tried. Let's talk about the challenges, the difficulties, the things that have gone wrong, or could go wrong, or almost went wrong but didn't. Because space is hard. Space is hostile. And keeping a spacecraft functional for decades, across billions of miles, is an extraordinary challenge. Voyager has had problems, many problems. Instruments have failed. The photopolarimeter, which measured light polarization, stopped working early on. The planetary radio astronomy instrument had issues. The plasma spectrometer eventually gave out. One by one, systems have degraded, shut down, stopped responding. The engineers have adapted. They've reconfigured the spacecraft, turned off non-essential systems, rerouted power, found workarounds. There was a time, back in 2020, when Voyager 2's primary radio transmitter failed. Suddenly, there was no signal, no data, just silence. The engineers switched to the backup transmitter. It worked. The signal returned. Crisis averted. But that backup is the last one. There are no more redundancies. If it fails, that's it. Voyager 2 goes silent. Voyager 1 has had its own issues. Glitches, strange behavior. Times when it sent back corrupted data, or data that didn't make sense. In 2022, Voyager 1 started sending back attitude control data that was clearly wrong. The spacecraft seemed confused about its orientation. But the signal was still strong, still stable. The spacecraft was still functioning. It was just sending back bad data. The engineers investigated. They found the problem. A computer was routing the data through the wrong system. They uploaded a patch, a fix, and the data returned to normal. Think about that for a moment. A spacecraft 15 billion miles away, decades old, with computer systems designed in the 1970s. And engineers on Earth were able to diagnose a problem, write a software fix, upload it across that immense distance, and make the spacecraft functional again. That's astonishing. That's a kind of magic, honestly. The magic of engineering, of careful design, of thinking through problems and finding solutions, even when the problem is farther away than anything has ever been. But every fix takes time. The signal delay alone is enormous. At Voyager's distance, it takes about 22 hours for a signal to reach the spacecraft, and another 22 hours for the response to come back. That's a 44-hour round trip. So if you send a command, you wait almost 2 days to find out if it worked. And if it didn't work, if something went wrong, you wait another 2 days to try again. You can't troubleshoot in real time. You can't have a conversation. You send a command, then you wait. And hope. And watch the data when it finally arrives to see if the problem is fixed. That requires patience, calm, the ability to sit with uncertainty for days at a time. And it requires trust, trust in the spacecraft, trust in the systems, trust that the commands you send will be executed correctly, even though you can't be there to supervise. That's the reality of deep space missions. You're not in control, not really. You can guide, you can suggest, but ultimately, the spacecraft is on its own, and you have to trust that it will do what it's supposed to do. Most of the time, it does. Voyager has been remarkably reliable, far more reliable than anyone expected. It was designed for a 5-year mission, and it's now been operating for almost 50 years. That's 10 times longer than planned, 10 times longer than the engineers promised. That's a success, an overwhelming success. But it's also a reminder of how uncertain these missions are, how much depends on luck, on things not breaking, on systems holding together longer than they were designed to, because we can't repair them. We can't send a crew out to fix a broken antenna or replace a failing component. Once a spacecraft leaves Earth, it's on its own, permanently. If something breaks, you work around it, or you lose the spacecraft. Those are the only options. And we've lost spacecraft, many of them. Not to mention missions that failed at launch, or failed to reach orbit, or failed to achieve their objectives. Mars is littered with the debris of failed missions. Landers that crashed, probes that lost communication, rovers that got stuck or froze or simply stopped working. Space is unforgiving. It doesn't care about your plans. It doesn't care about your budget or your timeline or your hopes. It just is. Cold, empty, hostile to machinery, hostile to life. And yet, we keep trying. We keep launching. We keep reaching outward. Because the alternative, staying home, not exploring, not learning, feels worse. Feels like giving up. Like accepting limits we don't have to accept. So we build better spacecraft. We learn from failures. We improve designs. We add redundancy. We test and test and test, hoping to catch problems before launch, before it's too late to fix them. And sometimes it works. Sometimes the spacecraft lasts longer than expected, achieves more than planned, sends back data for decades. And sometimes it doesn't. Sometimes the spacecraft fails. Sometimes the mission ends early. Sometimes we lose contact and we never know why. That's exploration. That's the nature of pushing boundaries. You don't know what will happen. You can't guarantee success. You can only try and hope and adapt when things go wrong. Let's think about what comes next. What happens after Voyager? After New Horizons? After the current generation of spacecraft falls silent? Are we going to send more? Are we going to keep pushing outward? Or was this a brief moment, a few decades in the late 20th and early 21st centuries, when we reached beyond the planets and then stopped? It's hard to say. Space exploration is expensive. It's slow. The results are delayed. The benefits are abstract. It's hard to justify spending billions of dollars on missions that won't return data for decades, when there are so many immediate problems to solve here on Earth. And yet, there are plans, proposals, ideas. There's talk of sending a dedicated interstellar probe, a spacecraft specifically designed to study the heliosphere, the heliopause, the interstellar medium. Not just a planetary mission that happens to keep going, but a mission whose primary goal is to leave the solar system and study what's owned beyond. Such a probe could carry better instruments, more modern technology, more power. It could last longer, send back more data, answer questions that Voyager couldn't. But it's still just talk, just proposals. There's no funded mission, no launch date, just ideas and studies and hopes. There are also more ambitious proposals. Ideas that push the boundaries of what's technically possible, maybe even what's physically possible. The Breakthrough Starshot project, which we mentioned earlier. Tiny probes pushed by powerful lasers, accelerated to 20% of the speed of light, fast enough to reach Proxima Centauri in 20 years. If that works, if it's actually achievable, it would change everything. It would make interstellar travel, at least for small probes, something that happens within a human lifetime. Something you could watch launch and watch arrive. But it's incredibly difficult. The engineering challenges are enormous. The laser would have to be absurdly powerful. The sail would have to be absurdly light and strong. The probe would have to survive the journey, survive the impacts, survive the radiation, and still function when it arrives. And then there's the question of communication. How do you send data back from 4 light years away, using a probe that weighs less than a paperclip? That has no room for a large antenna, no room for a powerful transmitter, no room for much of anything. Maybe you use the laser itself, reflect it back, use the sail as a mirror, send tiny pulses of light, encoding data aimed at Earth. If the receivers are sensitive enough, maybe it could work. Or maybe not. Maybe it's too hard. Maybe the distances are too great. Maybe the data gets lost in the noise and the probe arrives but can't tell us what it found. That would be frustrating. To send something all that way, to reach another star, and then have no way to know what it's seeing. But even that would be an achievement. Proof that we can cross interstellar space, that we can reach other stars, that the journey is possible even if the communication isn't. And maybe that's enough. Maybe the first step is just proving it can be done, and then we figure out the rest later. We improve the technology. We find better ways to communicate. We send larger probes, more capable probes, probes that can send back real data. It's a process, a long process. But it starts with the first attempt, the first success. Even if that success is partial, even if it leaves questions unanswered. That's how exploration works. You don't wait until everything is perfect. You don't wait until you have all the answers. You start, you try, you learn from what happens, and you try again. Voyager is part of that process, part of that learning. It showed us what's possible. It showed us how far we can go with current technology. It showed us the boundaries, the challenges, the limitations. And it showed us that those limitations aren't absolute. That with creativity, with engineering, with patience, we can push them. We can go farther than we thought. We can last longer than we expected. And if Voyager can do that, maybe the next spacecraft can do even more. Maybe it can go farther, last longer, send back more data. And maybe, eventually, we'll send something that not only leaves the solar system, but arrives somewhere. Somewhere new. Somewhere strange. Somewhere we've never been. That's the dream. That's the goal. Not just to leave, but to arrive, to see, to know. And maybe, just maybe, we're taking the first slow steps toward making that dream real. For now, though, we have Voyager, and Pioneer, and New Horizons, and Parker, maybe, someday. 6 spacecraft, 6 tiny objects moving through unimaginable distances. 6 pieces of us reaching into the dark. It's not much, but it's a beginning. And sometimes, that's all you need. This is ZzZscience, thinking tonight about journeys, about machines that travel farther than we can follow, about signals that fade, about voices that go quiet, and about the strange, persistent human impulse to reach outward, even knowing we might not hear back, even knowing the message might never arrive. We send them anyway, the spacecraft, the signals, the messages. We send them because we can, because we wonder, because the distance is there and we want to cross it. And maybe that's enough of a reason. Maybe it always has been. And so we come to the quieter part of the question. Not the technical part, not the distances or the speeds or the boundaries. We've talked about those. We've thought about them. We've looked at what they mean. But now, something softer, something harder to measure. Whether we can truly leave. Not just in space, not just by crossing lines or reaching certain distances, but in some deeper sense, in a way that feels complete, final, real. Because leaving is more than distance, isn't it? You can be far from something and still be connected to it, still shaped by it, still defined by it, in ways you might not even notice. A tree can grow far from the seed it came from, but it carries the pattern, the DNA, the instructions. Everything about what it is came from that seed, even if the seed is long gone, even if the tree never returns to that place. And maybe we're like that. Maybe the solar system is the seed. And no matter how far we go, we carry it. We carry the fact of having come from here, of being shaped by this particular star, this particular arrangement of planets, this particular moment in cosmic time. We're creatures of Earth, of water and oxygen and a narrow range of temperatures, of days that are 24 hours long, of a sun that's yellow-white and not too hot and not too cold, of a moon that stabilizes our spin, of a magnetosphere that shields us, of an atmosphere that filters radiation. All of that shaped us, made us what we are. Not just our bodies, but our perceptions, our sense of time, our sense of scale, what feels normal to us, what feels safe. And when we leave, do we leave that behind? Or do we carry it? We carry it. Of course we carry it. We can't not carry it. If we send humans to another star, they'll need Earth conditions, Earth air, Earth gravity or something close to it, Earth food or something that mimics it, Earth light, Earth temperature, Earth everything. Because we're adapted to Earth. We can't survive without recreating Earth, at least in miniature, wherever we go. So we don't really leave Earth, we take it with us. We build little Earths inside metal shells and send those outward. Little bubbles of home, drifting through the void. And maybe that's fine. Maybe that's enough. You don't have to leave something behind completely to say you've left. You can carry pieces of it, memories, echoes, fragments. But it does change what leaving means. It makes it softer, less absolute, less like an escape and more like an extension, a reaching out while still holding on. The spacecraft we've sent carry that too. Not biology, not life, but something. A sense of where they came from, the language of their design, the materials forged in Earth's factories, shaped by Earth's engineers. The messages, chosen by humans, reflecting human concerns, human hopes, human aesthetics. Voyager carries music from Earth, pictures from Earth, greetings in Earth languages. Even the golden record itself, a phonograph, is an Earth technology, an Earth way of storing information, an Earth assumption about how communication works. If anyone finds it, they won't just learn about Earth, they'll learn something about how Earth thinks, how Earth organizes information, what Earth values enough to send into the dark. And in that sense, Voyager hasn't left. Not entirely. It's still an emissary, still connected, still fundamentally of this place, even as it moves away from it. And maybe that's true for anything we send, anything we do. We can't escape our context. We can't become something completely other than what we are. We can only be what we are in a new location, carrying our history, our origins, our nature. So when we ask if we can truly leave the solar system, maybe we're asking the wrong question. Maybe the question isn't whether we can leave, but whether we need to. Whether leaving, in the absolute sense, is even desirable. Because there's value in connection, in knowing where you came from, in carrying your history forward rather than trying to shed it. Explorers throughout history have always carried their origins with them. They brought their languages, their customs, their technologies, their assumptions about the world. Sometimes that was destructive. Sometimes they imposed those things on others, erased other ways of being, other ways of knowing. But sometimes it was just what happened. Culture travels. Ideas travel. You can't be from somewhere and not carry that somewhere with you, at least a little. And in space, there's no one to impose on, at least not that we've found. The universe seems empty, vast and quiet and mostly empty. So carrying Earth with us isn't an imposition. It's just what we have, what we are, the only thing we can offer. And maybe that's okay. Maybe we don't need to leave Earth behind. Maybe we just need to expand where Earth is. Make it bigger. Make it include more places, more perspectives, more experiences. Earth used to be just Africa for us, just one small region. Then it became continents, oceans, the whole globe. And now Earth is starting to include space, the Moon a little, low orbit, the International Space Station, Mars maybe someday. And eventually, maybe Earth includes other stars. Not because we've left Earth, but because we've taken Earth with us, extended it, made it part of something larger. That's a different way to think about it. Not leaving as separation, but leaving as growth, like a child leaving home. They don't stop being their parents' child. They don't erase their childhood. They just grow beyond it, become more than it, add new experiences, new relationships, new parts of themselves that didn't exist before. But the origin is still there, still part of them, still shaping them, even as they become something new. Maybe interstellar travel is like that. We leave, but we don't leave behind. We grow, but we don't shed. We become more without becoming other. And perhaps that's the only way it can work, the only way that makes sense. Because you can't truly start over. You can't erase your past. You can only build on it, carry it forward. Let it be the foundation for whatever comes next. The sun will always be our star, the first one, the one we knew before we knew any others. And even if we stand on a planet orbiting Proxima Centauri, looking up at a different sky, the sun will still be there, faint, distant, just another star among thousands, but our star, the one we came from. And that will mean something. It will shape how we think about that new place, how we talk about it, how we understand ourselves in relation to it. We'll always be creatures of the sun, even when we're creatures of other suns too. And maybe that's beautiful. Maybe there's something comforting in that, in knowing that no matter how far you go, you carry home with you. You're never completely unmoored, never completely lost. There's a loneliness in space, an overwhelming, crushing loneliness. The distances are so large, the silence is so deep, the emptiness is so absolute. And if you're out there, crossing those distances, experiencing that silence, that emptiness, it might help to remember where you came from. To know that you're connected to something, that you're not just a random particle drifting through the void, but a continuation of something, a thread in a longer story. You're from Earth, from the sun, from this particular pocket of space and time. And that gives you context, meaning, identity. Without that, what are you? Just atoms rearranged, just matter moving. No different from a rock or a comet or a cloud of gas. But with that connection, you're more. You're a story, a history, a purpose. And maybe that's what we need if we're going to travel these distances. Not just propulsion and power and shielding, but meaning, connection. A reason to keep going when everything around you is empty and cold and dark. Home. The memory of home. The knowledge that you came from somewhere. That somewhere, far behind you, there's a place that made you, that knows you, that you're still, in some sense, part of. That might be what makes the journey bearable, what keeps you sane, what reminds you why you're doing this in the first place. So maybe we can't truly leave the solar system. Maybe we shouldn't want to. Maybe what we're really doing is extending it, stretching it, making it reach farther. The solar system isn't just a physical place. It's a concept, an identity, a way of understanding ourselves. And that can move, that can grow, that can encompass new places, new worlds, new stars. We're not leaving the solar system. We're taking it with us, making it larger, making it include more. And maybe, eventually, the solar system becomes just one node in a larger network. One home among many. One origin among many. And we'll be creatures of many suns, many worlds, many places. But this one will always be first, always be the root, always be where we started. And perhaps that's enough. Perhaps that's what leaving really means. Not forgetting, not severing, but growing beyond while still remembering, still honoring, still carrying forward. The machines are still moving, still drifting outward. Voyager and Pioneer and New Horizons, still traveling, still leaving in their way. And they carry us with them, our hopes, our questions, our curiosity. They're not just machines, they're ambassadors, representatives, pieces of us sent outward saying, we were here, we wondered, we tried, and they'll keep moving, for centuries, for millennia, long after we're gone, long after everything we know has changed beyond recognition. They'll still be out there, still carrying that message, still leaving, or having left, or somewhere in between. And maybe, someday, impossibly far in the future, one of them will encounter something, someone, something that finds it, examines it, wonders about it, and they'll see the golden record. They'll decode the images, listen to the sounds, try to understand what it means. And they'll learn about us, about Earth, about the sun, about this place we came from. And in that moment, even if it's 1 billion years from now, we'll still be connected, still part of the solar system, still identifiable as creatures of this particular star, this particular world. Because you can't erase your origins. You can only carry them forward, transform them, make them part of something larger. And that's what we're doing. That's what we've always done. That's what exploration is. Not leaving behind, but carrying forward, building on, growing beyond while still remaining rooted. So, will we ever truly leave the solar system? Yes. And no. And something in between. We'll travel beyond its boundaries. We'll cross into interstellar space. We'll move through regions where the sun's influence is faint and distant and barely measurable. But we'll still be of this place, still shaped by it, still connected to it in ways that matter. We'll leave, but we'll never fully leave. Not completely, not in the absolute sense. And perhaps that's the only honest answer, the only real one. We'll go, we'll keep going, as far as we can, as far as we're able. But we'll carry the sun with us, in our memories, in our biology, in our sense of what normal is, what home is, what matters. And maybe that's all right. Maybe that's how it should be. Maybe leaving isn't about cutting ties, it's about lengthening them, stretching them across distances that feel infinite, letting them grow thin but never quite breaking. A thread connecting us to where we came from, getting longer, fainter, harder to see, but still there, still real, still meaningful, still connecting us to home, even as we drift farther and farther into the dark. And the spacecraft are out there now, moving through that dark, carrying that connection, holding that thread. They're leaving, they've left, they're gone in some sense. But they're still ours, still part of us, still connected, and they always will be. Good night.